So it turns out there are a number of different reasons which cause the light to go not where we want it to go. The first one, and the one that actually dominates in the case of my Canon camera, and probably your Nikon as well, is just scattering. The idea is that there are minute imperfections in the lens, or grains of dust on it, or light bounces off the surface of the detector and bounces back and forth inside the camera a few times.
So Paul, it strikes me that our first piece of technology could just be a microfiber cloth, and you could clean your lens up a bit. Is that going to solve our problem here?
It certainly solves it a lot. I know I've often take a camera out on a cold weather, it mists over, but you get really bad scattered light. So this is a problem. It tends not to dominate for professional telescopes. The mirrors on the professional telescopes, here's the main mirror on the Gemini telescopes, are extremely good. You really need everything to be accurate to a tenth of the wavelength of light.
Right, so the Gemini mirror is 8.2 meters across, and it's accurate to a tenth of the wavelength of light, and the wavelength of light is less than a micron. So you're talking, you've got everything better than a 10 millionth of a meter across this 8.2 meters. Well, that's impressive. The technology is amazing.
It's impressive, but it's something we actually can do.
Yep.
You wouldn't have guessed ahead of time, but optical engineers are very smart people, and they know to
Okay,
do
so
it.
problem solved. We're done.
They even have high-tech dust cloths. In this case, they actually put carbon dioxide snow over the surface to clean it off. You don't really want to get a scrubbing cloth on something with that
Yeah, we'll
accuracy.
probably scratch it up. Okay, so we've got it solved. We're done.
Also, you might think, unfortunately, we have this problem. Again, we've seen this before, atmospheric seeing. And this turns out to be what limits you for ground-based telescopes. So how does this work? The image is blurry like this, and why is it blurry? Well, you've got to imagine all your rays coming down from space, and then you've got to imagine the atmosphere is not uniform. Some bits of it are hot and some bits are cold. So let's say we've got a cold bubble of air in front here. What's it going to do? Well,
so that cold bubble is going to have a higher index of refraction, so it's actually going to act like a lens in the way and cause the light to converge in the same way that if you shine it through a convex lens, it's going to converge, and that's going to mess up the image that you think you're seeing.
yes. Or you might have a bubble of hot air going in front, in which case it's acting as a diverging lens and spread the whole light out. And it won't be a very good lens, odds are, and these things are going to be drifting across the telescope at enormous speed, and they're going to be not nice simple shapes like I've shown here. So when you've got thermals, bubbles of hot and cold air, you're going to have trouble.
All right. And this is maybe one of the problems we have when we go up to Siding Spring Observatory here, where I routinely go up there and it's hot, and there you can literally see the stars twinkling above you, and we tend to have a pretty stirred up atmosphere that hasn't had a chance to settle as it has traveled 2,000 kilometers across the Australian continent before it gets to us.
Yes, you can usually see large numbers of wedge-tailed eagles circling around the mountain, which tells you there are definitely thermals coming off the side of the mountain to keep them aloft. There are better places on Earth than Siding Spring Observatory for this. For example, Mauna Kea in Hawaii, somewhere else you've both spent a lot of time, I imagine.
Yes.
And here you can see we're much higher up. There are no gum trees anymore. You're suffering from altitude sickness at this location. And here, there's a much smoother airflow, much fewer thermals. So, for example, here's an image I took of a particular region of the sky at Siding Spring Observatory.
Yep.
And here's an image of the same part of the sky I took using
Oh, go
telescope
back.
in Mauna Kea.
So this little bit you can really see. So one object is smeared together here, and then if we go up to Hawaii, it suddenly breaks into three objects. Now, Paul, why on earth were you looking for something changing? Why were you taking pictures of the same part of the sky from Hawaii and Australia?
Well, it turns out this part of the sky contains one of the 100 brightest radio sources in the entire sky, which is actually about there.
Ah.
And we took this picture and didn't see anything, so we went and took a deeper picture. And if you look just about very faintly over here, you can see a little red smudge, which actually we believe is a 12 billion light year away radio galaxy, which is producing the equivalent of a radio naked eye star.
Okay, so with clear sky or a non-turbulent sky from Hawaii, we can see further and see more clearly. But I note that these stars still aren't infinitely small, so we haven't quite solved our problem, perhaps.
Yes, I mean, the reason Mauna Kea is so good is because of there's a temperature inversion on the big island of Hawaii. You think of Hawaii, you think of your hula hula girls and rainforest and things like that. People always look askance at me when I arrive at the airport with my thick coat and woolly hat and mittens when they've got their surfboards. But of course up at the summit it's freezing cold. You can see in this time lapse taken from Gemini that most of the clouds are locked below the summit by this temperature inversion. So up at the summit it's actually very, very clear the thermals are locked below the temperature inversion.
So it's nice and smooth and steady, and all the turbulence and problems that we have in Australia are kept low below you.
Yes. So, I mean, a poor site like where I grew up in London, you might be talking 10 arc seconds seeing. Siding Spring Observatory is pretty good by that standard, maybe about 1 arc second seeing.
So when you say that, you mean that the angle that a star subtends in the sky is on order of 10 arc seconds. So that's 1/360th of a degree. So that's pretty small.
Yes, I mean, the human eye can only see about 100 arc minutes. So even that's why magnification works for things like binoculars, because
Right.
the human eye is not capable of seeing even very poor seeing. But when you get above a certain amount of magnification, about 100 or so, it doesn't help you anymore because you're being blurred by this. So what this means is if you get a light ray, it gets bent by about that amount, and for Siding Spring it's about 1 arc second. That would
Okay.
be a good observing site from 1970s.
Yep.
Similar for Mount Palomar and places like that. Mauna Kea or other good sites like the Atacama Desert in Chile, you might be talking about maybe 0.6 of an arc second at visible wavelengths. And that's still not going to be good enough because that's about all that separates a star from a planet.
Okay, so it strikes me that the best thing to do is get above the atmosphere and be done with it. Like the Hubble Space Telescope, our $2 billion telescope in the sky. And so, voila, problem solved.